and welcome to the Space for Kentucky. This particular series is a roundtable that is focused on growing the space industry. It's about networking, education, social support, and support for those who are reaching for the stars. And each Space for Kentucky has a different theme. The next several, the last one and this one, were all focused on spaceport development, bringing it to your community. And we are going to continue that theme. So spaceports are where space begins. And that's why I am so passionate about it. I am passionate about spaceports, and I believe that it can bring about innovation, education, and inspiration to an area while providing an opportunity for economic growth. In addition to my podcast and my position at the Transportation Cabinet, I am an author, and my second book focuses on spaceports. And that's how passionate I am about the spaceport industry and what I think it can do to an economy. Also, too, I work with Global Spaceport Alliance. I want to see Kentucky actually have a space there. And one of the things that is coming up is the Spaceport Summit. And if you feel about spaceports like I do, please make sure you're there. It's on January 29th. The keynote speaker to the Spaceport Summit is Jim Bridenstine. I am a big fan of his. He was the administrator to NASA, and he is also an elected official. Space mobility is the very next day, and then Spacecom launches for 2 days. I am a speaker for the workforce development panel, and I am moderating that at Spacecom. So please do join me for that. It's going to be a good one. Let's represent. A lot of times with these particular things, they have groups of different companies come in, or different states, different countries. So let's let Kentucky represent. We have a lot to offer. We have aerospace manufacturing is one of our biggest industries, and I think it has a lot to offer the space industry. Let's make sure that they know who Kentucky is at Spacecom. Couple of the speakers today I've also interviewed on my podcast. So if you want to know more about what it is they do, Christopher Allison was on one with Aerospace, Oscar was on one with InterFlight Global, and Arturo and David Alexander with Houston Spaceport were on the last Space for Kentucky. They also have an interview as well. So in part one, to give you a little bit of a recap, we had Houston Spaceport talking about how they were able to take $21 million of airport infrastructure money and change it into $5 billion with a B, $billion in contracts. They have been extremely successful. They are a horizontal launch spaceport, and they have education that comes to the spaceport, which is the Rice Space Institute with Dr. David Alexander was also speaking on that. And then Spaceport America talked about how to do the legwork before you launch into a spaceport, how to do the economic impact studies. And they just had one come out that showed the economic impact to their area as a result of the spaceport being built. Francis Walker from Corgan was here from London, England, and he was talking about how to design an airport. He is one of the global forerunners of airport design. And then Oscar Garcia was talking about the value for point to point. He is going to kick us off tonight and talking about what kind of aircraft go point to point. And just to give you a little bit of what a point to point is, it is the network of spaceports that will enable us to go from one area to the other in about an hour and a half. So he's going to talk to you about the type of aircraft that would do that as well. The next time we have a Space for Kentucky will tentatively be about February 29th, and it will be focusing on alternative fuels. There's a lot of conversation going on right now about the cadence of rockets and what it's doing to the environment. And there is a lot of research and some phenomenal things going on with alternative fuels. So I want to definitely bring those to your attention. And that's in aerospace, with aviation, and with space launch. If you want to get notified, please sign up for notifications. Go to spaceforkentucky.com and there's a button to be added to the list. There's also all the past meetings there. And for example, the education session that we had has a whole bunch of free links on how to get education into the classroom. So this is part 2, space vehicles. I am coining a phrase. I don't know if it's ever been done, but let's do it now, is Aerocraft. We have Aerospace, which is aviation and it's space. So a lot of the aircraft we're going to talk about tonight are both. You know, your aviation aircraft, they need air. Air is the core of their title. And so they need air in order to fly. Well, with the space vehicles, there is no air in space. So they have a different kind of engine. I'm calling them Aerocraft because that covers the different aerospace vehicles. Tonight, we have Oscar Garcia with InterFlight Global. He's going to be talking to us about the point-to-point type of different aircraft, which is suborbital, hypersonic, and supersonic. We have Christopher Allison with Sierra Space, and he's going to be talking about the craft that comes down that's going to make space manufacturing something that is viable and is going to be very exciting, all the stuff that will be able to be brought down. Khaki Rodway is from Dawn Aerospace, and she's going to be talking about a different kind of aircraft that places like University of Louisville, University of Kentucky, wherever you're located, where your universities are, that they can launch from a regular runway. It can do studies and stuff. So it's almost like having space in your own backyard and at your disposal. And then Mary Stringer is here, and she is going to be talking to us about the X-59 Quesst, which is a low boom flight aircraft that NASA is creating. And they're going to be doing some testing soon, which, if all goes well, fingers crossed, then we will see supersonic and hypersonic be able to go across land. And that's going to change the game for aviation and for everything. I'm very excited. We will be starting the evening off with Oscar Garcia. And let me tell you a little bit about him. He is the chairman and the CEO of InterFlight Global Corporation. His company focuses on senior level consultancy, board advocacy, and project design in the areas of strategy, enterprise development, finance, sales, and operations. Oscar is a frequent commenter, presenter, panelist, chairman, and consultant to mainstream audio visual media, press, and as well as aerospace, aeronautics, specialized news reporters worldwide. And he will be presenting on hypersonic, supersonic, and suborbital aircraft. So take it away, Oscar.
Thank you very much, Izzy. It's a pleasure being here with you today and with my friends as well on the screen and on the session. And I appreciate very much your podcast, Izzy, because we're transmitting and communicating here to the mainstream public in a very, very easy to understand way that is very needed if we are going to make the high-speed transportation in aerospace mainstream subject that people can enjoy being a part of. So let me share my screen, and I have a few slides to show you some of our views from our company and our activities regarding the future of point-to-point transportation. So in about 10 or 12 minutes, let me give you a briefing on how IFG and the Fast Forward Group, which is a think tank that we finance pro bono, is non-for-profit, and we're trying to harness the momentum about the point-to-point flight conversation. And one of the unique things about this group is that we cover all the segments of high-speed point-to-point, from supersonic to hypersonic to orbital. That makes us unique. We have about 300 members, and basically we are trying to see how from the space economy, the big slice of the space economy, how we can help to add a module to it, which is the point-to-point future transportation. Depending on how you look at it, most people would agree the commercial space industry is about $500 billion this year and growing quickly. Well, the big surprise is that the high-speed point-to-point industry is potentially as big or even bigger than that $500 billion. According to some investment banks, very, very well known, they are estimating the point-to-point transportation industry approaching $0.8 trillion. So when you add those two, we are well in excess of $1 trillion industry. So the Fast Forward group is a pre-competitive study research development group, and we look at different aspects of point-to-point transportation from conceptual designs to future networks. One of the unique things about our group is that we look at supersonic, hypersonic, and orbital as a continuum, as some of the features and characteristics of these point-to-point speed segments share many things in common, such as standards, safety, regulations. So we try to not to duplicate things and try to get the point-to-point conversation between airports or spaceports streamlined as possible. The beginning of the point-to-point story comes with the space tourism revolution that we've seen in the last 10, 15 years. We applaud companies like Blue Origin and Virgin for having proven the concept that we can go up and down safely and show space tourists how beautiful the view is from space. What we are trying to do from there is take it a step further. And once the spaceports are capable of launching missions up and down into space, we would like to see if we can start connecting them. And one thing that we are trying to do, and I think is important, and that's why I love your podcast, Izzy, because we need to go from our world of engineering technology, which is exciting, but it's complicated for the mainstream public, into a simplified world where the mainstream public who travels by air today can say, hey, travel through space could be simple, safe, reliable, and get a change from industry push to a market pull. When people demand, people ask for this type of flying and this type of travel. We have in our group a lot of the stakeholders in this industry. One of them is SpaceX, and we applaud their vision for their Starship concept. Probably some of you have seen their video. They show every city pair in the world connected in less than an hour. And that has triggered a lot of attention from the public saying, okay, no more 20-hour flight tortures. We could go to the other side of the world very quickly and even come back in a business day. The economic impact is very evident. It's a big industry in the making. I like to say that it's important that we look at space point-to-point in the context of aviation, air transportation point-to-point, and use the transonic world we live in today as a baseline to build into the point-to-point through high atmosphere, hypersonic, and then into space. But basically, the opportunity of point-to-point is beyond the financial case for the operators that fly these vehicles. We could change the economic development case of the world. And city pairs, countries, regions in the world that are poorly connected or not developing economically the way they should, with this type of capability, we could start adding value to, in general, the whole economic condition of the world. There's been many iterations on projects since 2001, approximately. So about 20-something years later, I think we are at the point where we have some tailwinds, and we might be able to see in this next few years, certainly within this decade, demonstrations of point-to-point in supersonic. That's why I'm so excited about X-59, Mary. Hypersonics, just visited with Hermes Hypersonics here in Atlanta yesterday. I'm convinced there is going to be a hypersonic demonstration within months with their quarter-horse vehicle. Last but not least, Orbital. Starship tried a couple of weeks ago, right as we had our workshop in West Texas. didn't work, but it will work very soon. And when we do those 3 demonstrations, we will have proven the concept of point-to-point at all speed levels is feasible. And from there on, it's just a matter of working on technical details and the technical development needed to connect the world. I'll leave you with a concept of these are all the spaceports in our nation, and now we look at them independently. Our goal at Fast Forward is to start connecting and creating a network of spaceports, just like the airports did in the beginning of aviation. And what happens is that connecting spaceports, where 1 + 1 would be equal 2, is not like that. It's probably 1 + 1 = 4. It's synergistic. It incites investment, incites political and socioeconomic incentives and economic development. From up and down at spaceports to point-to-point or spaceport to spaceport, as we call it, I think this is the decade where many of the few decades we've all been working on this will materialize. People here on this podcast are better qualified than anyone to share some of those future vistas. So thank you very much.
And I would like to point out, first of all, tell us the difference between hypersonic and supersonic and suborbital, because a lot of the audience may not know this.
Supersonic is any vehicle that flies in the atmosphere and flies between Mach 1 and 3, which is 1 to 3 times the speed of sound. There are many ways to look at this, but for simplicity, a hypersonic would start probably at Mach 4, between Mach 4 and Mach 10, but we usually qualify hypersonics inside the atmosphere, atmospheric flight. Anything above Mach 10 probably enters into orbital or suborbital space flight. Those could probably be good brackets to think of in simple terms, but there are other ways to look at it as well.
Now, in the map that you showed 2 different maps. You showed one from Bryce, that was the worldwide network that exists right now, and you showed the United States. And there are 13 spaceports that are in the United States, but that is not how many are working on developing spaceports. There are a lot of states working on, from everywhere from Yuma to outside Chicago. The Quad Cities are developing a spaceport. Las Vegas is developing them. Maine is developing them. So there's a lot of players that are entering into this field. It takes a long time to get an airport built, just an airport, a general aviation airport. To get a spaceport, we're talking probably 10 to 15 years if we have the go-ahead right now.
14 licensed spaceports in America, and as far as I know, 12 more in the making. And horizontal spaceports need runways. Runways take a while to build. Vertical launch pads are probably quicker. What is interesting is that many airports in our nation are suitable to be expanded or adding a module as a spaceport. I think there are 6 of them already in place. And if we look at those facilities as the way forward, we can have a very robust network of spaceports very quickly. I'm optimistic that the FAA and licensing agencies will respond to the demand with speed and with efficiency. I know the developers and the capital investors into spaceports are very quick, and I'm optimistic that we'll be able to increase the building of spaceports as industry and the business demands.
Thank you, Oscar. So I am very excited to introduce to you Christopher Allison. He is the Senior Government Relations Manager for Aerospace. Now, I want to tell you that right where I'm sitting, I have a poster of the Dream Chaser on my wall that I look at every time I do anything regarding space. So I am a big fan of that aircraft. And Christopher Allison has been my guest on other things. He was on my podcast, and he is in support of the Dream Chaser Orbital Vehicle Program. He has served as the federal agency's integration lead and landing site coordinator. In recent years, Mr. Allison has represented Aerospace to the FAA, the Department of State, the federal launch ranges, coordinating compliance with government requirements and regulations in support of the planned Dream Chaser launches and landings. In his tenure, Mr. Allison has represented Aerospace on several aviation rulemaking committees discussing topics of the commercial space regulations and integration into the national aerospace system. He has served as the chair of the Commercial Spaceflight Federation and is AIA's regulatory committees and has advised Sierra Space representation on ComStat. This is a game changer here for a lot of things, including aerospace manufacturing. This is where the goods come back down, and he's going to talk to us about it tonight. So take it away, Christopher.
All right. Well, thank you so much for that introduction. Excited to be here and on this topic of spaceports. And as kind of my bio shows, I've been in the space policy and regulatory world for a while. I've eaten and breathed this topic for a long time, and I'm really excited to kind of see the trajectory of where we are and the number of spaceports that are appearing. And a little bit of what I'll talk about today from Sierra Space's perspective is our goal to have a worldwide network of spaceports that supports our operations, but then allows us to build kind of this highway of commerce to and from space. And part of what we're doing at Sierra Space is beyond just the transportation, but it's also the destination in space that we are creating to create, or the need for these roadways, if you will, between spaceports here on the surface of the Earth and different points of access in space. So just a little bit about our vision as a company at Sierra Space. We're here to enable humanity to begin new civilizations in space, right? So building this infrastructure, these highways to be able to get goods, but also people to and from space and enable a more robust, sustained presence in space for humans. Another core part of our mission, though, is that we are building these platforms in space to improve life on Earth. There's been a lot of fundamental research done on the International Space Station, led by NASA and the ISS National Lab, that has shown that there are unique features, unique physical phenomena that occur in the microgravity environment that can lead to next generation drug discovery, next generation materials that, with the absence of gravity, are possible, and that here on Earth are either challenging or impossible. And when you take gravity out of the equation, sometimes it unlocks new solutions. So one thing that we're firm believers in is when you're faced solving a problem here on Earth, sometimes the solution is to look up to space, and we want to provide that infrastructure and that access. So how we are doing that within our company, we're focused on kind of three disruptive commercial product lines. So I mentioned the transportation side, and I'll get into the details of that. And that's really our intersection point with what we're talking about here is spaceports and that network that we're building here globally. Secondly, we have our space destinations. So this is those points of destination or the purpose to go to and from space. And this is really where we want to build the baseline of commerce in space. And then our space applications group, which is our technology centers and a lot of the components and the intellectual property that goes into building, this network of transportation and destination. So some of the key elements within this ecosystem that we're building, we have our Dream Chaser space plane, and I'll talk more about that. We have our Life Habitat, which stands for Large Integrated Flexible Environment. So this is our innovative bandable module that goes as the main building block of our space stations or our destinations in space. We have Shooting Star, which is essentially a service module that attaches to Dream Chaser, but we are designing it to be modular and versatile to be able to expand out into the space ecosystem. And then on the application side, we are developing rocket engine technology, power generation, pointing and motion control, all the building blocks that we need to be able to go and execute these large integrated systems in this ecosystem. So focusing a little bit on space transportation and our core vehicle of Dream Chaser, the first vehicle is called Tenacity. But we always like to point out how it's done today. And it's been, frankly, the same approach for the last 60 years, which is capsule launched on top of a vehicle that enters ballistically and goes through high G during reentry. And some of these novel technologies I was talking about are these opportunities in space for drug discovery, advanced material generation, and manufacturing rely on the absence of gravity, and then to put it on a vehicle that then goes through 8 times gravity is kind of counterproductive. And so we've designed Dream Chaser to kind of revolutionize this advancement in terms of space transportation. And so you can see from this view here, or this graphic, that Dream Chaser looks like an airplane, but it is not an airplane by any means, but it does integrate into similar infrastructure that commercial aviation that we're all mostly accustomed to here on this call would integrate with. So we do land horizontally on a runway. We're quite a bit smaller in terms of size of the vehicle than space shuttle, so we can integrate with more runways around the world. We require a runway that a 737 would land on, just as an example. But we don't have air-breathing propulsion on the vehicle. So when we come back, we are essentially a glider during reentry and as we approach a runway. So a little bit about Dream Chaser. So each vehicle that we develop is designed for high reusability, so 15 plus missions per vehicle, nearly 6 tons plus of cargo capability to and from Earth. And then that G-force, so the force of gravity during reentry, we have about 1.5 times the force of gravity during reentry, so which is quite a bit less than a ballistic reentry of a capsule, as an example, because we're able to control our attitude and we have lift on the vehicle during reentry. Other novelty that we have on the vehicle that is important to us to be able to integrate into a broader spectrum of spaceports here on Earth is that we have zero toxic fuels, so no hypergolic fuels, fuels that have low toxicity, so that we can integrate into that infrastructure without a lot of special bespoke equipment specific to our operation. So a little bit on the destination side of why we go to space, we have a partnership with another space company called Blue Origin. We are developing a platform called Orbital Reef, and what this is intended to be is the next generation space station, a follow-on to the International Space Station to support NASA's mission, but as well as open up commercial commerce in space as well. On the road to get there, one of the key pieces that we have that we're developing right now is our life habitat. And so this is that expandable module I talked about. Just as an example, the ISS right now, which is composed of rigid structures. So the pressurized volumes on ISS are rigid in nature, which means they launched in the same configuration that they're installed on orbit in terms of volume. It took 42 launches to assemble the entire space station. And so if you add up all the pressurized volume in the space station, a single life habitat module that I'm showing here in this photo is about 1/3 the pressurized volume of ISS. So in a matter of 4 launches, we can have the equivalent pressurized volume to ISS compared to 42 that it took NASA to assemble it over several years. So right there in itself is some innovation that we're bringing and how we're lowering the barrier or the cost barrier to access to space. We actually have some exciting news we just posted on social media. So we have a full size test article of this vehicle going to a burst test. So we are going to intentionally pressurize the module to structural failure to prove out safety margins. So that test will be coming up in a few weeks, and we'll have videos released of that, but it's going to be exciting. We've done 4 subscale third size tests of that to date, and those videos are out on the internet. They're quite thrilling if you like to see things blow up. I mentioned building this station, this destination in space, is not just the next space station, but as a platform for business of product innovation. So what we're looking at within this once inflated 3-story building, essentially in space, is creating next generation laboratories, taking what we're accustomed to for research and development here on Earth and implementing that in space, again, with the focus of removing gravity from the equation. We found through work done on ISS that gravity influences things that we do here on Earth, whether that's differentiation or certain processes in semiconductor manufacturing. And so we're looking to use access to microgravity to create novel goods in these areas and then be able to move those to and from the surface of the Earth in order to benefit markets back here on Earth and humans back here on Earth. And then on the space application side, so I mentioned this is kind of all of the pieces that build into these larger integrated systems. Things that we do are launch adapters, separation systems, docking systems, different electrical power systems, pointing control mechanisms, flight and thruster, vector control, thermal control. So all the engineering and very technical, detailed work and components that go into assembling these really cool systems so that we can go enable these different business models. So that's the end of my charts, but just a few other thoughts I have on spaceports and kind of building off of Oscar's remarks. And I mentioned that I've been involved with spaceports for a long time. I've spoken at the Global Spaceport Alliance meetings in the past. I'm really excited to see how spaceports are starting to proliferate, not only in the United States, but also around the world. And that's key to us, right? We want to be able to integrate into a network of spaceports to be able to service different customer needs. I think there's a lot of questions around the business case of a spaceport. And my personal opinion and my view on it is that each spaceport, just like you have airports, right, that are differentiated in terms of like, what is the purpose of going there? A lot of us go on business trips to particular airports because there's an industrial base or an ecosystem there that we need to go visit. And so I envision a similar kind of economic balance of spaceports in the future where you have different spaceports that have specialized capability, whether that's access to certain distribution channels here on Earth for commodities in space, or spaceports that are a hub of tourist activity that is either the beginning or the end of a trip to space, or as we really look into the future, point-to-point transportation, and how they all have their own kind of differentiated industrial base in order to drive commerce. And our vehicle is intended to be able to integrate across all of those and support different modes of commerce and these different business models. So I appreciate the opportunity to kind of just share some of our thoughts and what we're working on here at Aerospace, and open to any questions, Izzy, if there's things you feel I missed.
And I would like to first point out, well, what does this mean for Kentucky? So how does this apply to here? One of the companies that we have here is called Space Tango. They're out of Lexington. And one of the things that they create or that they're working on developing is artificial retinas that create sight for people that suffer from macular degeneration. So Sierra Space in the Dream Chaser will be able to bring back that technology so that a hospital that's nearby a spaceport, hint, hint, wink, wink, will be able to benefit from that particular technology coming back and how that will change life for those people that are suffering it. And if you would like to go back to one of the things you said about the pressure in the Dream Chaser compared to other ways of bringing those products down and how does that impact it, just if you would just touch on that again real quick.
No, absolutely. So, I mean, the case of the artificial retinas is a great example. The reason why there's an advantage to creating these or producing them in space is because there's no gravity. So you can do this thin layer deposition and build up the structure in a three-dimensional form without it getting deformed from the factors of gravity. And so you put all this work into developing this like very pristine, very delicate item. If bringing it back to Earth puts it through an extremely harsh environment, that kind of undoes the point of going to space to do it in the first place. And so we were very conscious in developing Dream Chaser and the guidance around how Dream Chaser re-enters the atmosphere so that we can, one, take advantage of access to space, but then two, be able to bring these things back to Earth in a condition that they're still usable. So we're really excited for those opportunities moving forward. And then further, because we interface with a runway similar to what a 737 can land on, as we start to work through the regulatory hurdles and improve reliability.
I think we lost him. He froze. All right. Yeah. Well, what he's talking about is that there's different AAA regulations that make it to where you need a license to be able to land the Dream Chaser, and that would be a horizontal landing license. So they take off though vertically as of right now, and we will not be able to ask him any questions, but what he is doing is extremely interesting, and I'm a big fan. So.
Yes.
I think I'm back. Sorry, I got disconnected there for a second.
There you go.
Yes.
There you go.
Yeah.
Okay, I just talked about landing licenses with the FAA.
I think you did a great job.
Yes, if I may, you mentioned Kentucky. There's a company in Kentucky called UPS that could be very
just
interesting.
a little one. Yes.
In understanding these up and down transportation capabilities, and one day point to point and freight and package and vital items just in time are a great example of possible users in the future. So that's right on your backyard.
Thank you so much, Christopher. And again, like I said, huge fan. Can't get enough of the Dream Chaser. I look at it all the time. So next we have Khaki Rodway, who has roots in Kentucky. And she is the space plane sales and operations director for Dawn Aerospace on the U.S. side. The MK2 Aurora is Dawn Aerospace's first entry into the suborbital frontier and the first stage demonstrator for their two-stage to orbit vehicle. The commercial version of this remotely piloted, which the Dream Chaser is also remotely piloted, is a reusable rocket plane that is designed to take off multiple times a day from a runway. The MK2 will take off horizontally, fly a parabolic trajectory at Mach 3, and glide back to a horizontal landing at the originating site or downrange, which is huge. And the vehicle 3-unit volume can contain and expose payloads in upper atmosphere. It is a flexible platform with various mission possibilities, including, I'm not going to pronounce this correct, aeronomy, Earth observation, which is huge when we start getting into the climate crisis that we're undergoing, education and research in space science, space weather, and technology development. The MK2 is the first in a series of vehicles that will merge the world of rockets and aviation to access space in a whole new way. Khaki, please take it away.
Thank you, Izzy. It's great to be here. Really appreciate this opportunity. Really appreciate talking about space in Kentucky, as Izzy mentioned. I have family there. I was born anyway, in a place called Kentuckiana, which is right there in Louisville. I wanted to talk to you today about what we call the Mark II Aurora. It is, to Oscar's definition, both supersonic and suborbital. And Izzy, I really like the Aerocraft definition that you gave, because what we find, spaceplane actually kind of means different things to different people. So we are an aircraft with a rocket engine and with the performance of a rocket. We're not a rocket or launch vehicle with wings. So we fly like an airplane, we maneuver like an airplane, and we can do a number of things. So let me just talk about Dawn, what we are, what we do. We're about, actually, I think this might be a little outdated on the head count. We're probably about 130 right now. We have locations in New Zealand, which is our headquarters, the Netherlands, and the US. As of, let's see, was it last week? We have 69 thrusters in space. So we get our revenue from in-space propulsion. And so we build the entire propulsion systems for satellites. We have been on 12 launches, most recently Transporter 9. In fact, all transporter missions, we have had our thrusters on those vehicles. And as far as the Mark II goes, we've had 50 flights of this airframe. 47 of those were with a jet engine and 3 were with a rocket engine. And those 3 were over the course of 3 days. So we flew every day in that time period. And like I said, we have revenue with our in-space propulsion. So we have customers. At our core, we're a space transportation company. So building a network, much like you build a, say, transit system. New York City has the famous subway. We're building this transportation network from Earth to space. And I kind of do have to point out here, when we designed this diagram, we were thinking we go, Earth, and then we're looking at kind of the orbits around Earth, and eventually we'll get to deep space. We're actually bypassing all of this stuff here, and we're going to send some thrusters to deep space with Astroforge. So Astroforge will be going up and going to mine an asteroid using our propulsion systems. The spaceplane, or it's called rocket-powered aircraft, or rocket-powered aerocraft, even better. So this is the development of where we are. So as I said, we built this airframe put a jet engine on it. And then the next phase where we are right now is with the Mark II and the rocket engine on it. And so just like an aircraft, just like aircraft qualifications, you push the envelope. As Izzy said, horizontal takeoff, horizontal landing. That lets us do a lot of things, or at least a lot of maneuverability, a lot of flexibility, a lot of testing. We'll push it up. Right now, we'll be certified to fly to 20 kilometers. We fly in New Zealand. I'll get to that in a minute. So we work with the Civil Aviation Authority there, and ultimately with the New Zealand Space Agency. We'll go up a little more till we get to 100 kilometers. Then down the line, about 4 or 5 years from now, we're going to build a bigger vehicle that has an expendable second stage that will launch 250 kilograms to LEO. But at the same time, much like with the Mark II, we'll be able to carry 250 kilograms into suborbital space. So not necessarily, when you talk about Earth observation, for example, there's a lot of instruments that are way bigger than 5 kilos. This is something where we could put an instrument way bigger on the Mark II and carry it. Still going to suborbital, still going to 100 kilometers. And here's just an example of the difference in size. So this is the Mark II, and this is the Mark III. What is it? What's the Mark II? So as I said, rocket powered, it's remotely piloted. As Izzy said, it's reusable, highly reusable. We can do on-demand missions or on-demand flights, kind of anywhere. And I'll get to that too. Horizontal takeoff, horizontal landing. The operations are fully contained. That's one thing I do want to mention is when we go out to our runway, we have a trailer. It's very much like a trailer that you see, say, hot rod cars or cars that are, being transported to a racetrack. We put the vehicle in here. It's small. It's about 5 meters, less than 5 meters in length. If you imagine, it's about 24 feet. Quite small. We have the computers, basically mission control is in that trailer as well. We go out to the launch site, unload it, and then we go. So we just need a 1,000-meter runway, almost 3,300 feet. And when you talk about Earth observation, this is a good complement to that Earth observation, because think about it this way. You have high-resolution imagers on satellites, and those satellites are 450 kilometers in altitude, the lowest ones anyway. You take the same resolution, put it at 100 kilometers, that resolution is going to be that much better. You're going to be getting some really sharp images. So I'm going to just show you this video. So this is our vehicle. This is our vehicle flying. It's not CGI, it's real. It's just New Zealand. I'm not going to read you the specs, but we do have specs on the website. So if you want to take a look at them, the payload, as I said, on Mark II, it's on the smaller side, but still enables us to do a lot of things there. Vehicle specs, Mach, I think we're at 3.6 at this point in terms of our speed. We will have microgravity time, comparable to some of the other suborbital vehicles like New Shepard and Virgin Galactic. We get 3 minutes microgravity time. So on the rocket engines, if you're interested in that, here's just that comparison of what we do. Our flights are considerably less than actually even, or comparable as in a sense to the balloons. We got a flight time that's longer than New Shepard, shorter than Spaceship Two, actually about the same as sounding rockets. I want to say here, in comparison to sounding rockets, because Izzy, when you talk about aeronomy, which is atmospheric science, this is where the atmospheric scientists get very excited, because sounding rockets enable you to take in situ measurements in the environment, in the atmosphere, but very quickly. So a sounding rocket will just go straight through the atmosphere. So you may get, say, just a few data points. With Dawn, because we can expose this payload to the environment, we can go in and actually take samples all the way down from 100 kilometers to the ground. And because we're in Aerocraft, we don't have to come down in a parabolic way. In fact, normal way anyways, because it's glide back landing, is going to be kind of this spiral method until we hit the runway. You kind of saw it there as we flew over Lake Khaki. That pattern can be kind of whatever the researcher wants it to be. When you talk about mission applications, the technology development is also really something people are very interested in. Education, of course. You talk about uses for universities and university consortium. So a lot of universities, especially the major geological, oceanographic institutions, have their own ship. They have their own research vessel. Picture universities having their own space research vehicle at a site that is close to them. it is a very real possibility. And we're working on that as we speak. And then the other thing that we think this is another application that we think this will be very good with is disaster response and recovery. So because we can fly on demand, because we need a small runway, we can have this vehicle at various locations. I mean, imagine if we had it in every state, for example, or we had it in disaster-prone states, which I suppose this time, I don't know, maybe I shouldn't say that because disaster-prone states are nationwide at this point. This vehicle can go up very quickly and get images and look at the area with if you have a high resolution imager, you get some really high resolution images that can inform the first responders on the ground. And where can we fly? Well, I'm going to show that map that Oscar showed again. Anywhere. So anywhere there is a horizontal runway that is 3,300 feet in length, we can fly. This was just a Google map search that I did for airports in Kentucky. I'll leave you with that. I'll be actually very interested in finding out how many of these airports could accommodate something like the Mark II. And then after that, very interested in having a discussion of how we get the Mark II there. Because our intent is not just to build one Mark II, is to build multiple numbers of Mark.
In Kentucky alone, there's 2 international airports because Cincinnati is actually in northern Kentucky. So we're one of the very few areas can say that. And then we have, I think it's 59 general aviation airports with a new one in Gallatin County that believe that their runway was built at 5,000 feet. So I think quite a few of them would be able to accommodate. Thank you so much. I am very excited about this because this makes space a little bit closer. You know, you take some of the more rural airports and then all of a sudden, if they have this type of technology that the university in that area can utilize, well, how much more attractive is that university? You know, how much more data and services is that area going to be able to present in regards to space and climate and all that if they have something like this at their disposal? This particular aircraft, I think, is wonderful, and 24 feet is still not small. But it's small for an aircraft for sure. So thank you so much, Khaki.
And there was one thing that I did want to say, because I've worked with Jerry Brodsky at Western Kentucky University, and he runs what is called the Kentucky Mesonet, which is a climate and weather network. So his idea was actually using the Mark II to measure lower atmosphere, because there's a big gap in the data in the Ohio Valley, in Kentucky, Indiana, West Virginia. There's not a lot of information that gets there. Using something like the Mark II, profilers, radiometers, instruments on the vehicle that can measure this data, this weather information, and the ability to fly it in multiple locations will give this Mesonet much greater detail, much greater modeling or information to do modeling. So it's things like that where we can change science in a sense by getting more data.
You know, as far as the disaster-prone states, yes, we can count ourselves among them. We had a huge tornado rip through Western Kentucky and a tsunami that happened in Eastern Kentucky within a year apart. 100-year events that were devastating. The climate is a big deal. It is a very big deal. Thank you so much, Khaki. We will continue on with Mary Stringer. Mary Stringer is the airworthiness certification lead for the X-59 Quesst, and that's with 2 S's. And that's a low boom flight demonstrator at NASA Langley Research Center. She is the lead. She leads collaborative, multidisciplined airworthiness requirement assessments, compliance planning, non-compliance hazard assessments, and criteria flight testing mapping across the entire team of technical leads to prepare for flight readiness review, airworthiness and flight safety review, and technical brief during a test flight. She's got a lot under her wings, and she has received a Bachelor of Electrical Engineering from the United States Naval Academy, and she also has a master's and is working on her PhD in Electrical and Computer Engineering from the University of Florida. And prior to joining NASA, Mary was commissioned active duty naval officer As a graduate student, she is a pathway intern to the U.S. Navy SPAWAR and now NAVWAR Atlantic 5.7 Space Systems Competency, a summer fellow at the Air Force Research Laboratory in the Space Vehicles Directorate. She is a licensed professional engineer and is an active member of IEEE and IAA. So welcome, Mary, and take it away.
Thank you so much, Izzy. I just want to first take the opportunity to tell you how much I appreciate you giving us this platform to share the amazing work that we're doing at NASA to revolutionize the commercial supersonic space or commercial supersonic flight. So sorry, you guys keep talking about space this whole time, and this presentation will have a slightly different flavor to it, but hopefully still a lot of information here that is interesting to you all. As Izzy said, my name is Mary Stringer. I'm the X-59 Airworthiness Certification Lead. I'm here to share with you a lot of the details of the X-59 flight demonstrator and the Quests mission that we're part of within NASA Aeronautics. I started with this project actually 10 years ago, originally as a flight controls engineer. Went off, did quite a few other things at NASA, and then came back to be their airworthiness lead a couple of years ago. So this project's really near and dear to my heart. Hopefully some of this is interesting to you all. And if you have questions at the end, Izzy, I'll happily entertain them. So this is a little video that the Quests mission office put together. I actually think it's a really cute little introduction. So that's a great little video, but you're probably wondering, why are we still talking about supersonic flight in 2023? And you saw that quick video, but what needs to be quieted and why is NASA doing it? Those are two of the biggest questions that I get all the time. So let's just jump back into history to when Chuck Yeager broke the speed of sound in 1946. So decades ago, right? So you're doing the math. And then it was in the 70s when supersonic technology moved to the commercial aviation world with the Concorde. They began flight tests around 1969, I believe, was their first flight. And it didn't take long for us to realize that there was going to be some problems with that, especially overland. Disruptive noise in the community, frequencies that impacted buildings, houses, structures, bridges. So the FAA moved quickly. And in 1973, they restricted supersonic flight over land. And ICAO followed similarly with worldwide restrictions. So if you do the math, that means that restriction's been in place for 50 years. They just had the 50th anniversary of that restriction this year in March. It's been a long time that this restriction has been in place, but what does that mean? That back even in the 70s, the airline industry had significantly less profitable routing for the Concorde. Obviously, it continued to operate transatlantically and other ocean legs, but overland supersonic speed restriction paired with some, efficiency issues, maintenance issues, that was really enough to end its tenure and not be replaced. And so that's where we are today, right? But even that was decades ago. So the question keeps coming up is, why is NASA working on this problem now in the 2020s? And the answer to that's actually really simple, and most people don't know it. The answer is we've been working on it for decades with our industry partners. It took quite a long time to build the models and understand how to shape an aircraft's outer mold line to quiet that sonic boom that was being so disruptive to all of our communities. And in many cases, the aerospace industry is more than capable of technical innovation on their own. We know that. We see that every day, especially on the space side these days. But when it comes to regulatory change, the government is looked at to lead that change in many cases. And really that's where we can step in and be super value added. So that's why it's important that NASA gets involved in these types of efforts, especially when they involve regulatory change. Just wanted to kind of make that statement there, because a lot of people ask, why is NASA spending taxpayer dollars on building this technology? And that's really why I think sometimes people miss the point there is those regulatory changes are actually really, really hard for industry to do on their own often. I need to go back to the timeline. So once we had built the confidence in our tools up high enough, NASA set out to build an aircraft that could do two things. One, use the aircraft to build a large database of sonic boom signatures and the corresponding community responses. What I mean by that is, how did the community perceive that sonic boom? And really that database will help the regulators change it from a speed restriction, which is what it is right now, right? No supersonic flight, that's speed, to a sound restriction, something where we don't care what the speed is as long as you stay lower than this particular sound threshold, right? And so that's the regulatory change that we're looking to see, and that this database of information would help with. And really, you can only do that if you build an airplane, fly it, and then collect that community response. So that's the first thing. The second is validating all of our models that we worked on with industry for sonic boom. There's two types of models. We'll talk about that a little bit more: near field models and then propagation models. But this is what really helps our US aviation industry build products for the airlines going forward. It means that if we validated these models, that they know that what they build with a certain outer mold line will get them a certain sound signature, right? So that important piece of what we're doing with X-59 and the Quesst mission is really important and oftentimes overlooked. That greatly reduces the developmental risks that our industry partners will see in the long run. So really, I kind of wanted to foot stomp that it's not just about changing the regulation, but it's making sure that our industry partners in the US are set up for success going forward and building products that actually will be successful. So let's talk about, the sonic boom itself, what it has been in the past for the Concorde. Really quickly, just give you a little bit of sort of science here behind it. When there's supersonic flight, there's pressure changes around the aircraft, and that pressure signature at that short distance below the supersonic aircraft, that's what I'm referring to when I say the near field models. So modeling what that pressure looks like around that aircraft. So that's one of the big models that I was talking about validating. As those waves start propagating, those shocks start to merge within a few hundred feet. And then by 1,000 feet, it turns into that classic N wave that we all learn in Aero 101. Even us electrical engineers are familiar with that, right? And then it holds that N wave as it travels all the way down to the ground. So that propagation there is the second model I was referring to. That's a big deal. A lot of things go into that. There's macro and micro impacts to what that wave looks like. Everything from, temperature, humidity, turbulence, all sorts of things. These are very, very, very complicated models. Just kind of wanted to drive that home, that this is kind of what it looks like now. So when you hear a sonic boom, sometimes military aircraft mistakenly, accidentally go over. I don't know if many of you have heard them before, but yes, this is kind of what's causing that pressure differential coming off that aircraft. So what's different? So what does X-59 do differently that these other existing aircraft don't? It's the shape of our aircraft. So essentially all of our tools helped us figure out what we needed to do to create a pressure signature that essentially generated very little merging of those shock waves as it propagated down to the ground. And so you can kind of see what happens here, that as it gets to the ground, it's no longer that sharp N wave that we're used to seeing from the Concorde and all of our military aircraft. It's now sort of a softened, more sinusoidal looking wave, right? And so ultimately that results in a significantly quieter sound that you hear on the ground. It also changes the frequency, which is what was impacting those buildings and the structures that we were talking about back in the 70s that everyone was up in arms about, rightfully so, right? So what kind of aircraft does that? So we were just talking that it took a lot of what kind of aircraft, is capable of doing that. And we talked about shaping the outer mold line, and really the design of this aircraft is driven by the outer mold line. As a flight controls researcher, it was the bane of my existence because it made it inherently quite unstable. NASA always talks about when we do X-planes, every X-plane just gets one miracle. And this miracle is hopefully going to be the quiet sonic boom. And it was not fun flight controls or anything like that. So yeah, this is what the outer mold line looks like. I won't drag you through the finer details of it. Max design, gross weights, 25,000 pounds. You can see that it's just shy of 100 feet. So it's quite long, but most of it's in the nose. Design Mach, which means that we 1.4, that's where we plan to cruise at. The perceived loudness, decibels, that's our design sound signature, essentially needs to be less than 75 PLDB. We'll talk a little bit more about that on the next couple of slides. And then for the engine and landing gear, this is a bit of a Franken monster. That's the F-18 engine we've got reconfigured for single engine use, and we're using F-16 Block 25 landing gear as well. So we did that to keep our costs down, to be able to utilize things that were already in the government's inventory, if you will. So take a look at the outer mold line, how long and thin it is, how the tail is shaped. All that really lends itself to the shaping of that sonic boom. This aircraft is designed specifically for that. So what does that mean in terms of sound? So let's put this all in perspective. So I talked about PLDB, that's perceived loudness decibels. It's a parameter that the acoustics folks use to try to help put things in perspective. DBs don't really do that. So perceived loudness is how a person perceives it in terms of its loudness. We're louder than a car door slam 100 feet away, but we're quieter than a basketball bounce. And then you can see their fireworks and gunshots are way up there. This is where our goal is to be. I can tell you that we were looking for a threshold, right? So we don't know where it is, but we're hoping that we designed well enough below where that threshold is that we're going to be able to find it. And we have the ability to change essentially what our sonic boom signature is by modifying things. Believe it or not, altitude impacts it, Mach impacts it, angle of attack impacts it, the position of the stab impacts it. So we have the ability to kind of drive that number up to try to look where the threshold is from when it starts being okay and where it stops being okay, and try to fit, pinpoint that in the data with the community response. And that's a big part of this. It's not just collecting numbers with sensors on the ground. We will be doing that. Every person who calls in or goes into the app, we'll talk a little bit about this during the community test, that's all geotagged. So we'll know where they are, what we predicted the sonic boom to be, where they are, what the sensors are saying it is, and then pair that with their response to whether it was acceptable or not. And ultimately, we hope that this is kind of down in the noise, right? That looks different for New York City than it does somewhere in the Midwest, but that's why we're going to be flying at a lot of different cities. So again, we'll talk about that a little bit more when we talk about what the mission's doing. I happen to be from the vehicle side of it, so you're getting a little bit more on the vehicle side in the beginning here. And then I put this slide in here just because since we were a little bit more space oriented, if you guys wanted to see what the boom signature, that N wave, looks like for a number of different other vehicles that might be of interest, the SR-71, the Concorde's on there, the F-104, and then of course the space shuttle. So you can see how different it is and what the normal range for military fighters is. 1 to 3 PSF. Again, this is a little bit different than what you're seeing over here. This is an overpressure chart, but again, gives you numbers to kind of compare where we are against that. So I won't go into the details. Unfortunately, I don't have time to explain what a focus boom is and some of the differences there, but just kind of from a visual perspective, seeing how different our signature looks, this gray line compared to other existing aircraft, I think is really important. So normally what I would love to do is take you to the aircraft and do the traditional engineer's walk around. That's what I do when I'm out with the aircraft all the time. Don't have the aircraft with me. There's some great things about the virtual world, but there's some downsides too. And actually, technically, she just rolled into paint, if you've seen the news very recently, but she rolled into paint a couple weeks ago. And so nobody's really standing next to her. But I will do a kind of a sort of a pseudo walk around and kind of point out a few things that might be of interest, some key features that kind of help us achieve what we're trying to do. I already told you that long nose, that super long nose, that is designed specifically to help us shape that the forward part of the shock wave. You can see the T-tail on the back is also to help us minimize that aft shock. And then we point out some of the inlet work. I can tell you that they spent a ton of time refining and refining again what that inlet looked like and the shaping of the aircraft around it to minimize the inlet spillage and its impact to the sonic booms. So all of that, tons and tons of care went into it. I've already talked about the engine and the gear, the control, the stability of this aircraft because of the shape of the outer mold line is not fantastic. So we obviously have digital controls, but there are a few things on the aircraft that also help us out. And that's the fixed canard. It helps us with our nose up trim and the aft deck and how we designed essentially that whole tail. Essentially, we simplified that to really help us make our stability and control efforts a lot less reduced. So again, I mentioned every X-plane can perform one miracle. This one's not about controls. We were very conservative in how we designed the control laws for this aircraft. The important thing here is new technology in terms of the sonic booms. So all that to say, you do need an aircraft that flies. It can't just be quiet. It actually has to get up in the air. We've done tons of aerodynamic performance testing, CFD, wind tunnel tests, tons of structural modeling, loads and stress tests, things like that. And then also, of course, handling qualities on the control side with the closed loop aircraft. Just some fun pictures of the testing that we've conducted. We've done low and high speed aerodynamic and propulsion airframe interaction wind tunnel tests. I was on the controls team back when this happened. These are all years and years ago. So I actually attended every single one of these tests. So fantastic experience for a really young engineer back then. We have multiple simulators. Lockheed Martin is the contractor that's doing the design build with us. They maintain one. That's the one you see on the left. And then NASA also maintains a full fidelity simulator as well. And the NASA one's actually the one that the pilots do training in. We do checkouts in the Lockheed Martin one. So we essentially run both of them at all times. We have enough pilots to get in the seats. We have three test pilots who are in training and do all of our checkouts for us, one Lockheed Martin and two NASA. The one that you see on the right is actually connected to the control room. So we can do control room testing before first flight ever even happens, where we can do kind of mission runs and things like that, where we can practice failures and things like that. Both of these simulators are really integral in us making it to first flight and being prepared for all of that from both the pilot standpoint as well as the engineers in the control rooms. There's a couple things. The external vision system, you can see the aircraft does not have great forward visibility. So we have two systems on board. One is the FVS, the forward vision system camera, and then the other is XVS, external vision. And very cool if you ever get the chance to see these operate in person. We've done test flights and other aircraft with the XVS. That's all NASA provided equipment and all very new and interesting. From a certification standpoint, which is my own, doing detect and avoid in the national airspace is a big deal. So using kind of pseudo vision like the external vision camera is actually pretty revolutionary, believe it or not. I won't spend much time here on the life support system. We've got a massive flight test instrumentation system. That's really interesting. If I had some time to talk about it, I just want to get us to the cool pictures. These are all for public release, but I don't believe that we've released these all pretty regularly. So some stuff here I don't think you'll be able to find anywhere else. So I kind of thought there were some cool pictures to show here back when we were in the jig, how we do machining, things like that. And then when the jig came out, you can see what it looked like at that point before all the wires and everything went in. That's when fab and integration really got underway. This is looking down the nose. This is our 414 engine before we lifted it in. Now we've lifted it, dropped it, lifted it, dropped it, taken the empennage, lower empennage off a million times now, but it was fun back when it happened the first time. We shipped the aircraft to Fort Worth to do some structural testing and some fuel testing. You can see photos from that here. Most of us and lead engineers went out for all of that. Then we shipped it back to the desert out in Palmdale. And that's when we continued to do wiring, some more systems installation, all of our gear checkouts happened. Of course, power on was a big deal before all of that. This is them installing the stabs, some crazy backbone wiring. You can see how intricate, how tiny it is. So space is very limited inside this aircraft. How we wire it was really important. Of course, we started some integrated system checkouts. You can see the upper empennage. That's where the engine lifts into, and then the lower empennage closes underneath it. So that's how we get our engine in and out. What we have left, we have some more system checkouts. Obviously, there's discoveries during every test that we have to go back, make modifications, do some regression testing, go back, bay closeouts. I just told you the paint's already underway. We've already finished ground vibration tests. We do have to finish structural coupling test, and then we'll roll right into engine runs. Aluminum bird testing. We do not have an iron bird, so we joke that it's the actual aluminum bird that we're testing on. So we're doing very iron bird-like tests on the actual aircraft. A lot of EMI work that's yet to come. And then that's when the taxi tests will start. We do have low speed and high speed, some very, very high speed that hopefully don't become accidental first flight. We all joke about that. I had this really lovely slide here so you can see how envelope expansion actually works for manned X-planes. You start slow, low and slow, and then you work your way out. I was going to share with you some of kind of what the integrated test blocks look like, but really it's flying qualities, loads, and flutter excitation, right? Those are the three things that you super care about, especially in the early phases of flight tests. So all of this is being done in phase one. This is my world. Phase two, once the aircraft, we know it's airworthy, we know it's safe, we'll start looking at the acoustics validation. Again, still all over flight test ranges. And that's where we start validating our near field and propagation models that I was really excited to share with you the information about. And phase three is probably what you care about the most. It's our community response. After phase one, after phase two, when we know that aircraft in and out, when we know it's absolutely safe, without a doubt, to be flying over communities, that's when we'll take it out and then fly these campaigns over multiple communities that are very representative of the United States. So they're in the process right now of doing the down select on what communities those are. A lot of factors go into it. They're looking for a wide variety so that we get response data that's representative of the entire United States, so that when we turn this over to the regulators, that they actually can make educated decisions about that sort of thing. So these are just some more information about the community test planning that we've got going on. Share with you the Quesst mission webpage that you can get more information about what we're doing and the community response tests that are going to be going on in the next couple of years. And I will just wrap it up here. So
It's the information that I hope everybody is, I mean, we're wanting this information for sure, because this is the next phase of aerospace. And there's a lot of change that's going to happen as a result of the work that you're doing and have done. Can you tell us when you think the next test, that big FAA test, when are you looking at that maybe happening in the future?
As first flight moves, like I said, the important thing to us right now, the most important thing is the safety of the communities that we'll be flying over. You do not want to rush through phase one.
No.
And you do not want to rush through these ground tests because we only have one aircraft. We believe that first flight will happen this year, and we'll probably wrap up phase one at the end of this year, is my guess. We're looking at 6 to 9 months. So if we go in early summer, you're looking at the end of the year, maybe early next year, depending on what discoveries there are, right? That's the flight test world. You hope there aren't any, but they're, probabilistically there will be. So, and then phase two will be the acoustic testing. So we probably won't be out in the communities for a couple of years. I can get with Kristen to get you the exact dates on what we're projecting, because I'm so aircraft centric. I've been, I'm mostly on the phase one, but I'll get her some answers for you on the community testing timelines that we're looking at right now based on the projections of finishing out safety of flight test. So.
And the one thing I would like to point out, there's a couple of reasons why this is impactful. Is one, that it enables us to go faster. So who wants to go faster on a plane? Yes,
Everyone.
We don't want to do those 20-hour flights. And we've been doing the same amount of flight time for decades now. So It is time. But another facet of this is because it's NASA. NASA has they share technology. So they're able to give a lot of, or do the spin-off technology. And is this qualify for spin-off?
Yeah, I mean, so one of the things, and I failed to mention this because I started rushing through everything, is that we had to show this is a single seat, ejection seat pilot, test pilot aircraft. This is not meant for, this isn't going to suddenly one day turn into a commercial aircraft. We had to show traceability to commercial aircraft. So we had to show that the boom signature on here was directly related to what it would look like on a commercial aircraft. And our partners are already in development on all those. I can tell you that. And, I know that we can't share too much from a proprietary standpoint, but my gosh, I've taken a bunch of them into the wind tunnel And they're charging ahead, hoping that, fingers crossed that we get these regulations changed soon. So, and that's the big impact. But yes, these tools, you're right. Perfect way of putting it is NASA has the ability to be transparent. So when we validate models and figure this all out, that immediately goes out to industry, U.S. industry, of course.
Right, which means that those tax dollars can go towards a new company using that technology to develop something in their wheelhouse. It's not like Boeing's doing it to where it's all proprietary and they don't have to share it with anybody. So, it being NASA is a huge deal. It's a huge deal. And
honestly, a lot of the propagation models, I can tell you, I can't rattle off the universities off the top of my head. I can have Kristen send them to you. But a lot of the universities are heavily integrated in those propagation models too. I can tell you that we have a number of university partners that are just fantastic academic think tanks that are such a big part of it too. So it's not just industry, it's also, academia is so heavily integrated in it as well.
Any questions before we wrap up this particular session tonight?
No, just a quick comment, Mary and Izzy. Not only this is good for America, this is good for the world. The whole world is watching, ICAO is watching, and the standard that X-59 will set up is going to permeate through the whole planet. And that, I want to emphasize how important that is. As investors look at building fast airplanes, they want to make sure they can operate across the world, not only in America. So thank you, Mary. Your team is amazing. And from the industry viewpoint, I can't wait till 2028, 2029, when that prohibition of supersonic flight over land has a standard under which it can be lifted. Thank you.
Right. Yeah. And absolutely. We are super heavily integrated in ICAO's subcommittees and things like that. They're actually they're waiting for our data. They're extremely excited to get it. So very good point. Well worth reiterating is, yes, I emphasize the United States, of course, because, that's where NASA represents, but so much bigger than that. It's a global thing.
So, where are we going to go? If we don't, we may be able to go from one coast to the other coast faster, but this is going to impact, going to Australia or going to, a whole lot of other places a lot faster, and it'll open up the world and opportunities to a lot more people.
I was just going to ask Sarah Blackman here. Did you get a chance to work with Ash Carter on some of the development of this project as well? Because they ran mutual aircraft development programs through the military at the same time. Yes, I was wondering if your teams got to work with Ash Carter's teams. They were working on the new bomber.
So I don't believe that there's this quiet supersonic technology, but I could be wrong. So I'll have to check about that offline for you, and we can get back to you. But there's a lot of atmospheric flight, development going on. But I think we are the only ones who are doing it this way. So, but that doesn't mean we haven't integrated with them in other ways, for sure. So there's
I was just curious. That was with the B-21 program with Northrop.
Right. Yeah. So the military has not been involved in this at all. And I have a military background, so that makes me sad sometimes, but this program is intentionally for the commercial side of it. So obviously the military,
very exciting.
The military will inherit anything that comes out of it, as they usually do, right? Thrust vectoring and so on and so forth. But
thank you so much. It's been amazing to hear, especially since you've been on this project for so long. So when did you start on it again?
I started in 2012 when we were in feasibility studies.
Wow.
So, that's why I said I got to go through all the wind tunnel testing, and as an electrical engineer, your first time in the wind tunnel, you're like, what is this? But over time, you pick everything up as my background is theory, so it was just interesting to see, the model build up and how all that worked. But then I left for a couple of years. I went off and did some Mars entry, descent, and landing work. I led a team of researchers doing aero database fusion with machine learning, And then I worked in the urban air mobility sector. I led up a team on automated flight and things like that. So I did a chunk and then came back. And so it's been so nice to come back, and it just feels like home sometimes on a project, you know.
Thank you all for spending your evening with us. And I hope that you come back for number 3, which is alternative fuels, which I think are a game changer as well. You know, if we want to have more cadence for space, then we have to have different fuels. So, and there's a lot going on in there. I would love to thank the speakers, Oscar Garcia with InterFlight Global Corporation, Christopher Allison with Aerospace, Khaki Rodway. I want to keep calling you Rodman. I'm sorry. So Khaki Rodway with Dawn Aerospace, and Mary Stringer with NASA. Thank you so much for sharing your evening with us. And I hope to see many of you at the Spaceport Summit in January 29th with the Spacecom and Space Mobility Conference. The next roundtable is roughly in February. I'm looking at February 29th. I hope you all have a wonderful holiday. Until then, see you all next year.